Hi all, I am Dr. Prathiba, working as an Associate Professor in Department of Electronics and Communication Engineering in Kamaraj College of Engineering and Technology. In today's session, let us see about Verilog code tutorial for the combinational circuit. So in this session, we are going to see through with half order how to write a Verilog code and how to write a test bench and the output waveform representation. Similar way, we can assume a simple combinational circuit and we can write the Verilog code using a gate level modeling. Moving to the first example, half order. In this half order, as we all know, half order is nothing but it has two inputs and two outputs. The two inputs here I have considered as a variable A and B. The output which I have used here for a half order is one is a sum and the other one is a carry. We all know the operators of an addition rule. In a basically for a binary addition, we have to remember these four concepts. One is 0 plus 0 is equivalent to 0, 0 plus 1 is 1, 1 plus 0 is equivalent to 1 and 1 plus 1 is equivalent to 1 0. Here this rest of all these three are being followed for my sum, and here this 1 is representing my carry output and the 0 is representing for the sum. We have to keep this operator rule in our mind and we have to fill the first one, which is called as a truth table. Here I am using a 2 input and 2 output. So my truth table will consist of input and output basically for a combinational circuit. So my inputs I have considered A and B and my outputs I have considered as C and S, a shorter form for sum and the carry. Now we have to pass all the input terms here. So since it's a 2 variables have been assigned here, we are going to consider 2 power 2 which is equivalent to 4 different combinations, nothing but 0 0, 0 1, 1 0 and 1 1. So we are going to fill the truth table using this operator rule. So here there are 2 inputs A and B and there are 2 outputs which is called as a carry, which is a variable which is used here as a C, and for sum I have used S. And when we are adding 2 component, your operator has to be kept in the mind. So 0 plus 0, the sum is 0 and carry is also 0. 0 plus 1, sum is equivalent to 1, carry is equivalent to 0. And 1 plus 0, sum is 1 and carry is equivalent to 0. 1 input, your carry is 1 and sum is equivalent to 0. So according to your operator, we have filled the truth table. Now after your, we want to have, for a gate level modeling, we have to have a combinational logic circuit to derive the Verilog code. So in order to get the expression, we are going to go for the simplification rule using K-map. So it's here input is a 2, so I am using a 2 variable A and B. So I am going to find out for carry, the similar process I am going to execute for my sum. So we are going to fill the min terms here. So my sum min term is equivalent to, this is nothing but for 0, 1, 2 and 3. So my min terms are 1 and 2. My carry min term is my 3. So we have extracted the sum and the carry min terms. We are going to fill it in the K map. So the carry is, the min term is 3. So 0, 1, 2 and 3. So in the cell number 3 I have filled the min term, and for 1 and 2 I have filled it for the sum term. So we are going to do the grouping. Here it is a single grouping. So this is my single grouping, and here it is only here also it is coming for the single grouping. So my carry is equivalent to S1, which is equivalent to A and B. This is my expression which is obtained for my carry, and for my sum S1 plus S2. So S1 is nothing but A bar B plus A B bar. So my sum is equivalent to A bar B plus A B bar, or it can be written as XOR gate. So A XOR of B. So we have derived the expression using the K-map simplification. Now we are going to write the Verilog code. So in the previous one we have derived with the expression of S carry, right? So now what we are going to do is we are going to write that equation. So what the equation we have obtained previous is sum is equivalent to A XOR of B, or A B bar plus A bar B. This is what we have derived from the previous one, and carries C is equivalent to A and B. Now what we are going to do here is we are going to write the gate level modeling for this half adder circuit. So here initially we can label the gates. So here I am using G1 and G2. So this is a and B are my input and sum and carry are my output. Here we are using XOR gate as well as AND gate. So starting with the Verilog module. So module, half adder, my output variables are S and C, my input variable is A and B, completing with the semicolon. Next one, declaration, input A and B, output S and C. So port declaration has been completed. Next we are going to start the operator. So here what we are going to do here is we are using XOR gate. So XOR label, we have written the G1 as my label. So G1, my output is sum and my input is A and B. So XOR gate has been completed. Next one we are going to write for the AND gate. So the keyword is AND, label we are writing G2, my output is C. So carry is my output, that is we have represented as a C. So C and A comma B. So we have completed for both the gates. So we are going to close the end module, right. So now we have written for the two gates, that is XOR gate as well as for the AND gate. Next one we are going to write the test bench. For writing the test bench, that is nothing but we are going to pass the input in order to write the test bench. So here the initial code will be started. Inside the parenthesis we have to pass all the inputs. So I am going to write the inputs. My variable is I have declared as capital A. So A is equivalent to what are the combinations of input is given. You can directly write it in a straight line with some delay. So here why we are giving a delay is, for this particular delay period your input will hold on with the initial one. Next input you are going to pass it as A is equivalent to 0, B is equivalent to 1, and here it will hold for 5 nanosecond. Next one is A is equivalent to 1, B is equivalent to 0 and followed with the delay. And the last one is A is equivalent to 1, B is equivalent to 1 for a delay period of 5 nanosecond. After the completing of all the test cases into your test bench, after passing all your inputs, you have to stop your input variable declaration. So what we are going to do here is I am going to write dollar symbol followed with a stop. What occurs here is the last output after 5 nanosecond it will stop. That is the rule for applying this one. Now for all the test cases we are going to see the waveform. So for the waveform you are going to give your input and you are going to test with your output. Now my input I am going to take it as A and B, my output is C and sum, right. So my input here it is 0 0 1 1. So I have to take it for a period for 5 nanosecond. For a 5 nanosecond, this I have considered for 5. So this is 10 nanosecond, this is 15 nanosecond and this is 20, because I have given a delay of 5 nanosecond. For initial of a 5 nanosecond, the first input will be taken into account. So my A, for A that is equivalent to 0, so 0. Next is it is equivalent to 0, so 0, and next one is 1, and then it is also 1, so again it is flowing to 1. So this is my input response for my A. Similarly I am going to draw for my B also. So 0, 1, 0 and 1. So this is my response of my input which has been fetched, and I have to check with my outputs. Here my output is, for a carry it is 0 0 0 1. So for 15 it is 0 0 0, then followed by 1. For sum it is equivalent to 0, 1, 1 and 0. So if we verify this one, so for the initial one 0 0 0 0. So when A and B is 0, your sum and carry is equivalent to 0 0. The similar way 0 1, your for 0 1 your carry is equivalent to 0 and your sum is equivalent to 1. So, this is the way which how we are going to write the waveform for the Verilog code. Similar process can be done for any combinational circuit like a full adder, also can be done for a half subtractor and full subtractor. Next, let us move on to the combinational circuit. Here I have taken a simple combinational circuit which consists of AND gate, NOT gate and an OR gate followed with an NOT gate. So, first thing is, in the previous part we have been reduced and there is no interconnection between one gate and another gate, but here looking through this, both the AND gate and the NOT gate is been connected to another one more gate which is an OR gate. So, if there is an interconnection between one gate with another gate, we are going to use an operator which is called as a data type, which is called as a wire. So, this we are going to declare it as a wire. So, I am taking this path which is connecting the AND gate and an OR gate as W1 and NOT gate and OR gate as W2. Then the same thing, this has been there. So, I am going to take it as W3. So, the interconnection between the gates is been labeled with the data type which is called as a wire. So, here I have used 3 wire connection W1, W2 and W3. Next, for our reference I have labeled what is my gate. So, these are my gates, 4 gates are being used. So, I have used G1, G2, G3 and G4 are my labels for the given combinational circuit. So, let us write a Verilog code for the given combinational circuit. For reference, I will just writing here. This is my W1, W2 and W3, right. Now, what we are going to do, we are going to write a Verilog code here. So, starting with module, I can give any name. So, I am writing a combinational. So, COMP comp. I am taking the variable inputs and our output declaration it is given as Y, input is given as A, B and C followed with semicolon. Next one is input declaration and output declaration. So, the inputs are A, B and C, all are single bit declaration. So, directly we can give the variable and output Y. After declaring the ports of input and output, we are going to write the connecting component which is called as the data type wire. So, wire, I am using 3 wire here, W1, W2 and W3, and the next one is we are going to go for the gates. AND gate is used in the initial one. So, AND gate, this is an operator, AND is an operator and G1 is a label of it, and my output is W1 and my inputs are A and B. Next gate is NOT gate. So, I am using the keyword NOT, label G2, my output is W2, comma, my input is C. Next followed, it has been given to the gate of OR gate. So, OR gate label is G3, OR gate output is given to W3 followed with an input W1 and W2. Now, the wire data type wire has been considered as an input. Next one is the last one is a NOT gate. So, NOT gate label is G4, my output is Y, my input is Y3. So, I have completed writing for all the gates, AND gate, NOT gate, OR gate and followed with the NOT gate. So, I have completed the statement. I am going to close the module. So, end module is used here. So, this is a simple way of writing using a gate level modeling. Similarly, we are going to write the test cases here. So, as I informed earlier, the test cases can also be written in a simple way like passing all the inputs. So, A is equivalent to 0, B is equivalent to 0, C is equivalent to 0 with the delay of 5 or 10, whatever the delay you want to give, you can give it here. I am considering 5 nanosecond and pass for all the test cases. So, the next case we are passing. So, we have completed passing all the 8 different combinations, because the input is 3, 2 power 3, 8 different combinations will be produced. So, 8 test cases have been considered, and then as I told earlier, to stop the execution we are using $stop. So, this is a test case which we have used for the given combinational circuit. Similar way, as we have seen in the earlier process, we also can go for drawing the output waveform. So, here we can draw the output waveform. I have drawn for A, B and C all my output combination 0, 0, 0 to 1, 1, 1. Now, I am going to execute what will be my output Y. So, for 0, 0, 0 of A, B and C, my output is 0. So, it will fall at the output 0. Next one is 1. So, I will moving to the 1. Next one is 0. Next one is 1. Next one is 0. Next one is 1. And the next 2 combinations are my 0 respective for the given circuit. So, I have drawn with respect to the given input my output waveform for the given circuit. Thank you all for watching this circuit.